I would like to present you our recent study of limb darkening computations, and also our first step to investigate how surface magnetic field affects the limb darkening. So the motivation here I presented is actually already said by Svetlana as well and others people. So the main idea is that limb darkening is important to interpret the planetary transit light curve. And if we add the atmosphere on top of the planet, right, this effect is also changes. So, and all of this is wavelength dependent, as was already said. So I just want to remind you very briefly. So we have limb darkening that is wavelength dependent. We have also depths, transit depth that is wavelength dependent. And to disentangle, or at least to have a very good transmission spectrum, we should have a very accurate limb darkening on different spectral regions. Yeah, okay. So why we are doing this limb darkening? Because we have very good code, MPS-ATLAS code. This is merged, parallelized, simplified ATLAS code. We merged ATLAS 9 and the very well-known ATLAS 9 code and DF-Sins and make it faster. So it parallelized everything like ODF, opacity distribution function, or model atmosphere, computational spectra. It's very flexible. We can change spectral grid we want to compute. It could be also high resolution. Now we can change different line lists and also some improvements in convergence criteria. Having this nice tool allowed us to compute a grid of model atmospheres and limb darkening, like a new grid and very fine grid. So here in the black dotted, I showed our grid compared to Phoenix with the red one or to the Mars with the blue one. You see, this is a region where actually also Svetlana showed where all known host star exists. So this grid is very fine in this region. And this was our purpose because we wanted to avoid interpolation and take just the closest limb darkening. This is an example of our model atmosphere. It's not all. In total, we have a lot. We have 2 different data sets, and each of them has more than 34,000 models. The first data set is contain model atmospheres for Graves and Saval abundances, 1998, and also their mixing length parameter alpha is constant. But we have another data set with the latest, with their newest Esplund abundances, Esplund et al. 2009, and also we allow our mixing length parameter to change for different metallicity, effective temperature, and lodging. We also include the overshoot of 1 pressure scale height. Okay, and here I just want to show you some example of limb darkening because we have many. For each of the model, we have limb darkening. Wavelength dependent. Here I showed you in the Kepler filter, so it convolved with the Kepler filter. Just an example. We also feed it with 2 different laws. It's a Fock coefficient law from Claret 2000, and also with the power 2 law. And having all these nice computations, it's very good to compare it to observations. And what we have here, we have some issues. This is observations from Max-Planck 2018. And this observation, so this is actually coefficients, observation minus computational. This coefficients comes from the power 2 law, but it's slightly modified. H1 is actually intensity at 0.5 mu. And this is a sample of Kepler star. This is a very well-known Kepler 17 that was already mentioned by Heidi. It's an active star, and it's an outlier here. So it's the comparison between, this was done, the comparison between observation and computation. Computation was done for 3D hydro simulation. This active star, and also we have some some drift here, some systematic shift, right? This, oh, sorry. So this Kepler star gives us an idea that maybe the magnetic field matter, that, and it can explain this outliers. So why it could happen, why it could matter, right? So magnetic field here is just an example how the cubes, the MURaM simulation by Beck et al. 2015, how the cube looks like when there is magnetic, or like this is hydrodynamical, and this is magnetic. And magnetic means that this is actually emergent intensity from G2 simulated atmospheric snapshot. And this is normalized to the mean intensity of the field-free simulation at each mu, so you don't see the limb darkening from here to here. Magnetic field is concentrated in the intergranular lane, and also due to the convective motion of plasma, and heats the atmosphere. It modifies the temperature and pressure structure of it. That's why it's so magnetic field is it heats the atmosphere, and the limb darkening becomes shallower. So now what we want to do, we wanted to compare our the 3D simulation, like 3D limb darkening, with solar observation. This is our first step because the sun should be as a reference. We have the solar spectrum here, and there are different stars. It's just randomly selected wavelengths where the naked and lab observations were made. These colors correspond to the colors of the lines here. So let's go to this plot. Sorry. Here we have the solid line. Solid line is our simulation for 100 Gauss. This is 3D simulation. The dashed line, this is 3D simulation, but with hydro. The stars, this is observations from Necklin labs, and the dotted or like field circles, this is our 1D simulation, 1D computation with MPS-ATLAS. From this plot,
2 minutes.
From this plot, you can see that actually our the 100 Gauss fit very well observation at different wavelengths. Our simulation, 1D simulation, is not very far away from here, but maybe it will be better to see when I plot the ratio of it. So here is the ratio. This is 1D simulation to be published in our paper. It's computational intensity divided by observational. And this is the ratio on different wavelengths. The color is the same as here. So this is the same wavelengths. The worst consistency we have for the very short wavelengths. This is 3D hydro simulation. And this is 3D simulations with 100 Gauss. So as we saw already here that it's very good agreement with observations, but in the ratio you see that's even better. So the best agreement between observations and simulation is when we use 3D computation and 3D CLV, limb darkening with 100 Gauss. So magnetic fields matter. So here I just wanted to tell you some messages to take with you. The main importance is we present a very fine grid of 1D model atmospheres and limb darkening at different filters and different wavelengths. Magnetic field matters, and our future steps is to provide a coarse 3D grid of limb darkening, including magnetic field. It's coarse because it's very computationally expensive, but we could also use our 1D simulations to interpolate for 3D. Okay, thank you very much for your attention. That's all.
Thank you very much. So I have one question here for you in Slido. So the ATLAS equation of state is known to be unreliable, outdated for low temperatures. Did you replace the original ATLAS equation of state with some newer version?
Yeah, we have a new version of, so our MPS-ATLAS is based actually on the newest, right? But so for cool star, we have the coolest if you go to the temperature grid, the coolest what we can see there is 3,500 Kelvin. We improve also the binning here, and we actually have a good agreement. We also compare with high resolution, so it's not, we have very good agreement.
Okay, thank you.